Hello there, and welcome to everyone joining us for this latest IoT Central webinar. I'm Clive Maxfield, everyone calls me Max, and I'll be your host. In addition to being a practicing engineer, I also act as a technology consultant, author, speaker, and educator. I'd like to start our webinar by thanking Canonical and Intel for sponsoring today's event. Canonical and Intel are both leading supporters of the IoT Central community, and we're very grateful to have them as sponsors. Today's webinar is entitled How Real-Time Linux Accelerates Industrial Transformation. Before we begin, I'd like to briefly review the format of today's proceedings. This event will be 1 hour long. We have two presenters who you'll meet in just a moment, and there'll be a question and answer session following the presentation. Feel free to ask questions at any time during the presentation using the questions feature in the control panel. I will be posing your questions on your behalf during the Q&A portion of today's event. So now I'm very pleased to turn this over to today's presenters. Whenever you're ready, Eduardo and Dieter, you can take it away.
Hello everyone and welcome to this webinar delivered by Intel and by Canonical. I am Edoardo Barbieri, Product Manager at Canonical, and together with me today we have Dieter from Intel. Hi Dieter.
Hi, I'm Dieter Kors. I work on our real-time and connectivity offerings on our real-time platforms at Intel.
Perfect. So today we will be covering a broad range of topics at the intersection between real-time Linux and the software-defined industry transformation that we are seeing in the market. So we will start by explaining what are the business benefits of such a transformation and what are the technology shifts behind the transformation. With this in mind, we will then introduce real time into the picture and we will tie it back to the broader market trends that we are seeing. So to understand real time, we will then go into details on how to achieve real time compute on Linux as well as at the silicon level. So Intel is one of the vendors delivering early TSN capabilities on their Ethernet solutions. And this is when Dieter will take over and discuss the public standard as well as the capability that they have of providing and delivering real time on their general compute SoCs. So we have a lot to cover and let's just get started. So this term Industry 4.0 describes the journey that industrial companies are taking toward a complete value chain transformation by digitizing essential functions within their vertical operation processes as well as with their horizontal partners in their value chains. And when talking about this Industry 4.0 trend, there are a lot of related concepts that point to the same aim and intent of transformation and digitization. So at the core of it, we want to move from a scenario with dedicated hardware performing one specific function toward a software-defined system delivering different functionalities. In turn, this will result in a much more dynamic environment with the flexibility within the factory or within any other implementation. But what's underlying the shift? So today, if we look at industrial platforms, we generally see very isolated networks. Often those are proprietary with the industrial field bus systems connecting the various specific dedicated setups that perform one single real-time function. Or in the server space, everything is firewalled between those networks. And such a legacy infrastructure poses barriers to data sharing and to two-way communication between the devices. So the transition that we are seeing in the market is a prerequisite of smart manufacturing or what is often referred to as autonomous industrial systems or next-gen factories. We are digitizing and modernizing our infrastructure to deliver on the promise of visibility and transparency in our manufacturing operations. We want to be able to monitor and control the physical devices and processes in the enterprise. But for this to happen, we need to transition from closed standards and interfaces to the embrace of open source software and modern IT solutions. So how does real time fit into this picture? the two IT/OT domains that we observe in the modern factories, they so far work separately and with completely different systems. So the firewall between IT and between OT is preventing Industry 4.0 solutions from taking place. And to fully benefit from Industry 4.0, the boundaries between operational technology like machine controls, the IT world, and the IoT, they need to be overcome. And we see Linux with real time playing a key role here with the Ethernet-based TSN. This is what enterprises and partners are looking for because the combination would enable quick reconfiguration and would allow the end user to exchange and use data for analytics from the various nodes. And in the past, different industrial PCs didn't necessarily support real-time capabilities. They were used mostly for HMIs, maybe some data gathering. But today, we are seeing increased demand, increased real-time compute demand in industrial PCs, driving some of those control systems. Of course, also PLCs are part of the story, and we see industrial servers acquiring real-time capabilities to do more of the factory level control pieces. So this same transition and the adoption of Linux with real time is occurring in process industries as well, from refineries to drilling. So overall, we're seeing industrial edge servers, industrial PCs, PLCs, robots, and drones, all with real-time requirements and supporting capabilities. So Linux and real-time, they're playing a role at the different levels that historically were in the factory. And some of those historically separate components are now coming together in the industrial PC. They are into a consolidated system with the Linux sitting on top of it and requiring real-time compute support. So this transition to a software-defined Industry 4.0, which is underpinned by open standards, by open interfaces, and the adoption of open source Linux with support for real time, is happening steadily and slowly. And I can't stress enough the importance of starting the transition as early as possible, because this will not occur overnight. It will be a slow progression. So I purposefully wanted to set the problem statement first before going into more details. But now that we have provided the necessary context to frame the rest of the conversation, let's look at the technology aspect of the transition and let's understand what makes a system real-time in the first place. And starting with the basics, a real-time system is time-bound with well-defined fixed time requirements. If the real-time system is unable to service its compute tasks within the specified upper boundary of time, so that processing is not done within the defined constraints, then the system has failed. And in the Linux kernel context, real-time denotes a deterministic response to an external event. And the processing of these time-sensitive workloads depends upon the capacity of the Linux system to respond to the events within a known and bounded interval of time. The goal being to minimize the response time. Now, I also want to caution the audience around some of the misconceptions around real-time, because a real-time operating system is not always necessary. It sounds promising for something to be real-time, usually because there is a performance connotation that comes with it, but we must really look at the actual consequences for missing a deadline and the latency requirements. And based on that, we should be able to answer whether or not they warrant real-time capabilities. So for instance, if a deadline is in the order of seconds, that's likely not going to be missed on a multi-gigahertz CPU with proper tuning. So there is a trade-off here. Real-time does not necessarily result in optimized performance, and we are rather looking at a deterministic response to an external event to minimize the response latency, not optimize throughput. So as I was highlighting, real-time Linux plays a role in the software-defined transition to Industry 4.0. And we see a wide variety of use cases across different markets. And, and I want to give you a high-level view of where real-time capabilities will be required. So industrial is a key market segment, and this is both in process automation, like the energy sector, petroleum and refineries, as well as in discrete automation, like in car manufacturing. You could imagine that to maintain the system integrity, to maintain the continued production, the PLCs in an assembly line must be able to process and to deliver data in real time, because a missed deadline could compromise the entire production line. Also, if we think about the effects of real time, about the consequences of a missed deadline being catastrophic, then all sort of other use cases and workloads can come to mind. So one can think of dedicated devices like life supporting medical equipment or medical robots in the healthcare industry. But also in telco, we also see the virtualized network functions, which are mission critical services in a telco infrastructure. And what we're seeing is that these network function virtualizations, they are taking root in the production environments of telco operators, and they often require support for real-time workloads. So there are many other broad market applications than the ones listed here, and this also implies that the requirements on the real-time performance will vary as a consequence. So enterprises require different levels of real-time tuning because of all the different latency requirements and cycle times that are needed for different use cases and verticals. For instance, a motion control for a robot will not require the same performance that a conveyor belt would require, and a CNC machinery with precision drilling, they would have very tight control loops. So it really depends on the function. You can see very low control cycles in PLCs with tight requirements, and the latency being stretched to microseconds. But we can also see those requirements being more relaxed and less stringent when looking at the synchronization between robots on a conveyor belt, for instance. All right, so now let's take another step further and let's delve deeper into the tech behind real time. And what is key to understand in this scenario is that we are looking at an overall real-time stack, from the underlying silicon to the operating system to the networking layer, the applications, and so on. Because a real-time kernel on its own will not make your system real-time. The rest of your hardware and your configuration, they have to be set up for it, and it takes careful tuning and understanding. Even the most efficient RTOS, the real-time operating system, they could be potentially ineffective in the presence of other latency sinks in the hardware or in the system. So just switching to a real-time kernel will not make your system real-time, because a real-time kernel is one component of a real-time system. And even with a real-time capable kernel, specific tuning for each distinct application is normally required. So in the next few slides, we will go deep into each layer of the stack represented here, including the lower levels of the illustration where our colleague from Intel will take the lead. So let's start with how to achieve real time at the OS, at the operating system level. So the scheduler of the Linux kernel has already several models available to balance the latency throughput trade-off. And depending on where you want to be on that spectrum, you can get closer to the guaranteed bounded response time and minimum latency that we want from a real-time kernel. So for instance, at the opposite side of that latency throughput trade-off, the non-preemption case is for server workloads, and this is the traditional Linux model, which maximizes the raw processing power of the kernel irrespective of the scheduling latencies. We also have preempt voluntary, and this model is intended for desktop use because of the quicker application reactions to user input. Another model available in the Linux kernel is preempt, And this option reduces the latency of the kernel by making the kernel code preemptible. And this allows reaction to interactive events by permitting a low priority process to be preempted. So I've used the term a few times already, but what does it even mean for an event to be preempted? Kernel preemption means that tasks can be interrupted. So if you imagine to have a process, it can be running in user mode until a hardware device may raise an interrupt in the scenario in this example. As a consequence of this interrupt, the process A will then switch to kernel mode and it will service the interrupt. The process will then resume execution in user mode, and each CPU model provides special instructions to switch from user mode to kernel mode and vice versa. So in this particular scenario, at this point, a process switch will take place and process B will start its execution in user mode. The issue with this picture is that when a user space process requests a kernel service, no other task can be scheduled to run until the original process has completed. So without preemption capabilities, scheduling can only take place after the first task completes its processing, which means that you can't have the deterministic response time because you have to wait for the completion of the original kernel request. So improving the flexibility to preempt or to interrupt tasks executing in the kernel would help to guarantee an upper boundary. So making the kernel preemptible means that while one process is running in the kernel, another process can interrupt the first one and be allowed to run even though the first process has not yet completed its service. So allowing preemption within the kernel would dramatically improve the capability to provide a deterministic response time. So the main characteristic of a preemptive kernel is that it can interrupt a lower priority process and assign the CPU to a higher priority one. And this concept of preemption takes me to the latest announcement by Canonical, real-time Ubuntu. So real-time Ubuntu is the end-to-end and robust Ubuntu which integrates the Preempter T real-time patches. And Preempter T is the name of the patches used to implement the priority scheduler and other supporting real-time mechanisms. So those patches are a set of modifications to the Linux kernel to change the scheduler from the default priority-based scheduler to one that is more sensitive to reducing latency, the way I just highlighted. So those patches, they are hosted at the Linux Foundation and they are not yet upstream. They are steadily being mainlined and is what partners and customers have been asking for. So by bringing commercial grade support to the real-time Ubuntu kernel production deployments, we want to enable enterprises to deliver mission-critical applications requiring the highest level of security and predictability. So real-time Ubuntu with the preemptor T patches will also continue to deliver the robust performance and the end-to-end security that our customers desire from the most widely used operating system among professional developers. But as I was mentioning, a real-time kernel is one component of a real-time stack. So this is the reason why Canonical and Intel are partnering on delivering real-time Ubuntu optimized on Intel Silicon. So now let's switch to the upcoming work that we will soon announce and to the more forward-looking part of the presentation. So Dieter, the floor is yours.
So thank you, Eduardo. So yeah, we are, from an Intel point of view, delivering already several generations of real-time capable platforms. And this one here shows the extent of what is currently out already in terms of covering the entry market, the client market with our core products, as well as the performance areas with some Xeon products. So real-time for us means time coordinate compute and TSN will be available and is available on all these platforms and will be available on future platforms as well. So with that, Eduardo, I think let's move into the next section here, where I really get into more detail on what Intel is delivering in terms of time-sensitive networking and Intel time-coordinated computing, and really Canonical and Intel have worked together of making sure that that is covered in the upcoming release for Ubuntu real-time for IA. So looking at real-time compute at the silicon layer, right? So Eduardo already mentioned that the OS is one critical piece of delivering a real-time system, but there is needs in the user space as well as needs in the hardware and firmware layer, right? What that means in the hardware and firmware layer, right? You need to prioritize the real-time workloads as they get processed on the silicon. You need to make sure that there's no interrupts from other workloads on that same silicon. You need to make sure that you allocate the right resources for that real-time workload and make sure that the synchronization, even within the SoC, between different elements of the SoC is guaranteed. So really making sure that you have all the different capabilities together on the SoC, and as the last bullet shows here, also providing the access to time-sensitive networks. In this space, we're really talking about IEEE TSN-capable networks over Ethernet, and in the future, actually also over 5G and Wi-Fi. So just a little bit more background on Intel TCC, so time coordinated computing, and IEEE TSN. We are striving to deliver both of those technologies on our platforms and have real-time support going forward. From a TSN point of view, TSN looks really at the network space of making sure that time-sensitive applications workloads get processed and have the priorities needed in the network. For that, you need time synchronization of making sure that different nodes on that network are nicely synchronized and are knowing what their times are. And from a timeliness point of view, making sure that you can schedule workloads and data as it goes through the network. TCC is basically the equivalent on our SoC itself. So when the data comes into our system, making sure that everything in the system is optimized to really deliver to the time-sensitive nature, to the deterministic needs that Eduardo was talking about early on. Again, even within the SoC, there's an element of time synchronization between different elements of the platform, as well as from a timeliness point of view, making sure that the processing, the latencies are kept low. Intel TCC is not a one IP in our platform that is there that handles real-time processes. What it really is a set of optimizations throughout the whole SoC to make sure that the real-time workloads are processed correctly. That means we have optimizations on the cache and memory side to make sure that the real-time workload has enough cache and memory allocated to process. It's important from a data processing throughout the SoC, going from memory to the CPU and so on, in terms of making sure there's no interrupts, right? Interrupts from another workload that might have, might not have the right priority, and making sure that that priority is assigned. Making sure that on every core where we process the real-time workloads, that we really have the priority for processing the real-time workload on the core where it's running on. From a clocks point of view, an SoC has many different clocks throughout the SoC, making sure that they are all synchronized, right? So making sure that they're working on the same time. And then from an I/O point of view, of really going out and helping the connection to the network, for example, that's another element where we have optimizations. So really, it is a general optimization for allowing real-time processing on a CPU where other workloads are running at the same time. And that really leads into what the main purpose of TCC is. It's what we call temporal isolation, making sure that when there's a real-time workload, in the example here, the real-time workload running on core 1 and core 2, and there's other workloads running on that same SoC, that you isolate those workloads from those other workloads running on the same system. And with that, have them run without any interruption with the right resources and so on. So that's really the key element of what TCC provides on our platform. The other element that is very important on the silicon side is the connection to the network. And as Eduardo said, a network that provides the capability of running general workloads over Ethernet and 5G and Wi-Fi going forward, as well as delivering to the requirements of real time from a deterministic time sensitive side is very important. So TSN delivers time synchronization across that network, traffic shaping, which really is a lot about scheduling what traffic is on that, so that real-time workloads can proceed through the network without interruptions, making sure that it always is available. So I think the preempt piece that Eduardo was talking about is certainly an element that plays into that, and then being able to configure that network going forward. So on all our platforms, we make sure that we have TSN capable Ethernet and 5G and Wi-Fi in the future available to our customers. That might be via a discrete Ethernet controller from Intel, or it might be over some integrated Ethernet ports that we have. But on all the platforms where we have real time, we have TSN available. So just looking at what that TSN offering is, it varies a little bit from platform to platform. What you see in the table below is the different platforms that I had in the earlier slide that we have real-time support on, and then what our options are for TSN support. Every platform that has real-time is validated with Intel i226 in the previous version, i225, 2.5 gig Ethernet that offers TSN. So that's our default available TSN option. And then some of our platforms with varying number of ports also have integrated Ethernet. Our focus is definitely on the discrete going forward. What does it mean to have TSN? So TSN is a summary term over many different specifications of that support real time, and not all of them are equal. There's for different industries or so, there's a base set of capabilities that are required. We are delivering that to that base set on all our platforms. Some of those are things that there's specific areas in the hardware, like the bottom three ones here that we deliver in the hardware and in the driver. Other ones have hardware and driver and a user space component to it, like 1ES, for example. And then there's, from a network management point of view, things that are just application level activities that are not directly in the silicon itself, but we offer the whole offering of that, making sure that the key TSN specifications are all covered. And with that, I will hand it back to Eduardo.
Right, thank you, Dieter. So this takes us to the end of this presentation, and we saw the steady transition from closed standards and closed interfaces and monolithic architectures, the steady transition toward the embrace of open source software and modern IT solutions in the context of Industry 4.0. And as we mentioned, real-time compute is at the core of this software-defined transformation. At Canonical, we recently announced the general availability of real-time Ubuntu with the upstream real-time patches applied And preempt-RT, which is the name of the patches to implement a priority scheduler and all other supporting real-time mechanisms in the Linux kernel, is steadily being mainlined and is the way that Linux achieves real-time support. But we also saw that a kernel on its own, it is only one component of a real-time system, so that even with the real-time capable kernel, specific tuning is still required for each distinct system. And to address the challenges when shipping embedded Linux with real-time capabilities in production, um, and to meet all the different requirements of a real-time software stack, the leading distribution for developers joined forces with the leading silicon manufacturers. So we are working with Intel on the remaining components of a real-time stack that Dieter went through, like Ethernet-based TSN and many others at the silicon level. So real-time Ubuntu is now production ready, and the upcoming images optimized on Intel hardware are an ideal commercial grade solution for enterprises engaging in large-scale deployments and shipping embedded Linux in production. So if your workloads require real-time compute, if you're working on a commercial project, reach out to our team at Canonical or at Intel for custom board enablement, for commercial support, for long-term maintenance and distribution. So thank you all for listening, and we will now open the floor for questions.
Well, thank you so much, Eduardo and Dieter. That was very interesting. I learnt a lot of things I didn't know. There's always something more to learn, but real time, yeah, very exciting. So now it's time for our Q&A session. We've got some excellent questions coming in. So I'm very eager to hear your insights on them. So the first question is, how does preempt RT affect the Linux kernel, beside providing a higher preemption than mainline?
Yeah, I can take that one, Max. Thanks for raising the question. So preempt-RT, as mentioned, is about increasing the so-called preemption level in the Linux kernel. And as we were saying, preemption is at the core of real-time Linux, and it consists in temporarily interrupting the current thread of execution so that you can have a higher priority event, you can process it in a timely manner. So with preempt-RT, increasing the what we call the preemptable code surface within the Linux kernel is what would dramatically affect the capacity to provide a deterministic response time to an external event. The challenge in making a preemptable kernel, however, lies in identifying all the locations in the Linux kernel where preemption must not occur. So those are the sections where the kernel developers must disable preemption. For instance, when two processes are trying to access the same data structures in critical sections, in those cases, kernel preemption must be disabled. And we want to, because enabling context switches in those scenarios could result in corrupted data. So preemption is one aspect of preempt-RT, and preempt-RT brings the capability of preemption to the Linux kernel, but it also implements a priority scheduler and other supporting real-time mechanisms. So it strives for full preemption in the Linux kernel, including in the critical sections of the kernel, except for very low level, very critical code paths like entry code and low level interrupt handling. So the goal, the objective of the preempt-RT patch set is to make all the code running in the kernel mode involuntarily preempted at all time, and doing so by bringing most of the execution context under the control of the scheduler. And there are several ways and approaches that preempt-RT uses to do exactly that. So beyond the idea of preemption on its own, preempt-RT, for instance, replaces locking primitives like spin locks with some variants that are aware of priority inheritance. So without going into too much details, but this enforces interrupt threading, it introduces mechanisms to break long non-preemptable sections in the kernel just one more, I guess, mechanisms that preemptively adopts to make the kernel deterministic involves replacing the mutexes in the mainline Linux kernel with what we call RT mutexes, and they again implement priority inheritance and priority inversion. So there are several supporting mechanisms next to preemption that are available in preemptivity.
Wow. I'm watching all these questions flooding in. There's no way we're going to get to all of them. I should point out, if we don't get to your questions, then Eduardo and Dieter have kindly said they will contact you directly afterwards to answer them. So don't worry if we run out of time. A quick one here. How do the technologies offered by Intel link to Ubuntu real-time?
Yeah, so I think
Dieter,
that's a question for me. Yeah. so really, what we have been doing together with Canonical is really working on making sure that every OS patch is first of all upstreamed, and then working with Canonical of making sure it's built into the Ubuntu real-time kernel, and working together on validating it the right way. So really, the linkage is via the upstreaming, via making sure that everything we have on our platform that is new is getting into the Ubuntu real-time kernel.
Okay. I think you actually covered a bit of this, Eduardo, but we've got Marco here from HTEC Group, and he asks, are we able to design parts of the system, user space, to rely on the RT capabilities of the kernel, and other parts which are not time sensitive to support other functionalities?
Yeah, so that's an excellent question. And as we were covering, the Linux kernel is one layer, right, in the software stack, and your user space applications, depending on your latency requirements, determining also on your use case and the hardware that you're running on, have to be tuned to be able to meet the specifications of your scenario. So there may be some cases where you may want to have more real-time sensitive applications at your user space level, where you may want to focus on tuning at that aspect. But in other scenario, your user space applications don't necessarily have to be real-time capable themselves. It may be the case that your latency requirements are not as stringent, and maybe the consequences of not meeting your deadlines are not as dire as in assembly line where you want to have continued production. And in that scenario, you may just rely on the real-time Linux capable kernel without affecting the upper layer of the user space applications. In general, if you want to have an enabled end-to-end software stack for real-time, so taking care of the silicon, the operating system, networking, user space applications, etc., and make sure that your hardware is enabled to run real-time Ubuntu, to make sure your applications are real-time capable, etc. We have entire field engineering teams at Canonical and at Intel to make sure that we can do exactly that. So to go over tuning, to go over enablement and certification on your specific use case and scenario for your applications. So to make sure that the requirements of your target applications are being met.
Yeah, Max, let me add something to that, right? So really, when we're talking about Industrial 4.0 and this software-defined environment, right, this combination of mixed criticality workloads is really what we're targeting with real-time support on Linux, right? It doesn't mean that the rest of Linux goes away. It just means that you also have the ability of adding real-time support on that as well, and managing the balance between the two.
Actually, you've touched on something. Two people have asked, I think, related questions. One says, who will provide real-time support, help with system design, and help debug real-time issues? And then somebody else asks, actually, it's the same person, I think. Debugging real-time systems or designing them requires a deep understanding of kernel subsystems, as well as core features like locking. Who provides this expertise to customers? Are there mainline kernel contributors or maintainers involved? So I think both of you might want to comment on that one, or those two.
I can maybe start on that one. It is, of course, interesting to hear the reference to mainline developers. Ubuntu being the most popular Linux OS, our own engineers are mainline developers themselves, so we contribute back to upstream, we contribute to the Linux kernel, and we also contribute to Ubuntu. So when it comes to the Linux kernel, when it comes to long-term support, CV patches, and making sure that the latest bug fixes are implemented, that is where the Canonical expertise comes in. So all of the operating system kernel layer is being taken care of by the Canonical experts, who are the publishers of the Ubuntu operating system. I don't know if Dieter, you had something to add to this one.
Yeah, and so from an Intel point of view, right, we're trying to make it as easy as possible for developers to use our capabilities, and one part of it is working with Canonical on Ubuntu real-time, right? But we also provide tuning guides for how to tune for real-time. So there's several pieces of support that we deliver on our platforms there, right, around real-time implementation.
And maybe just one final comment on this one. As we are on a journey together, Intel and Canonical, in the upcoming weeks and months, we will start publishing more information on some high-level tuning guides for real-time Ubuntu, some more maybe detailed, more technical informations regarding how to meet those latency requirements and how to affect the kernel. So as you keep the journey with us, you will also learn more how to achieve those targets yourself.
Very cool. Can there be a guaranteed maximum latency when RT is enabled in the kernel? And what is the maximum and typical latency?
Well, I'll take that one. So because it's real time is highly dependent on the hardware, on your use case, and the application and the silicon you're running on. Because of that, just providing a guarantee in abstract is not something that we do. So we do not provide a maximum guarantee, because that is strictly dependent on your hardware. So it is highly affected by tuning, it is affected by your user space applications, by the silicon, by the Linux kernel, etc. So those are all the reasons why we cannot just provide a number in abstract.
And I can add to that as well, right? So what Eduardo is saying is exactly right. What Intel is doing on our platforms, as a guideline, we provide a key performance indicator of what we believe can be achieved with our platform in a kind of worst case environment for a specific setup, right? So we provide the setup instructions and how we measure it just as a guideline, but naturally that's not a guarantee for maximum latency or so, but it provides what we see as a worst case scenario, and that can be customers under NDA with Intel have access to that.
Okay. And you touched on this, Dieter, in your presentation, because we saw multiple cores. But this question here: will real-time Ubuntu support multi-core processors and distributed RT threads over the cores? And here's the kicker: and if so, how does that work? In 10 words or less.
If you want to take
I can take a stab, right? First of all, yes, real-time support on multiple cores is certainly possible. In general, I think the target is to have a real-time workload run on one core and isolate that core, but we are operating on the assumption that you could have several real-time workloads on a core, at least in future platforms, and that you could have several cores loaded with real-time workloads. So there's no real restrictions to just one core can be real-time, but I think this threading between different cores certainly adds additional complications to it. So, but yes, it's possible. And I don't know, Eduardo, if you have anything on the west side on that.
No, I think that is exactly right. It is possible regarding maybe the lower level details of how it works. We will probably publish some more guidance, some more material on the topic, but it is something that can certainly be achieved, and that users can attempt. That when engaging in enablement and certification exercises with the Canonical, we can look at together to make sure that it is certified on your hardware and we are able to run those multi-core real-time processing workloads.
Okay. Are time-coordinated computing and time-sensitive networking working only available on Intel platforms? And also, are TCC and TSN available on all Intel platforms and SKUs?
Yeah, so TSN is a IEEE standard. So naturally that by itself means, no, it's not just an Intel product. We are one of the earlier companies that have TSN enabled products. But it's not only Intel. TCC, as I mentioned in the previous slides, is a specific technology or optimizations throughout our SoC on our Intel platform. So TCC is definitely an Intel specific offering that just delivers better latencies, better time synchronization, deterministic compute on our Intel platforms. So to the second part of the question, both Intel TSN, both TSN and Intel TCC are available on select platforms and SKUs. So not all Intel platforms are real-time capable, not all SKUs are real-time capable. So we publish a list of SKUs and platforms that are real-time capable. In general, we have about a 2-year cadence of platforms with time capability.
You see, that was one of the things that had never struck me before this presentation. I'm familiar with RTOSes, but I've always thought of them as something that runs on a fixed platform. I'd never thought about tweaking the platform, the processors, to be able to better serve the RTOS. So I think that's a very exciting development.
It is, and it's certainly a development needed for the kind of flexibility needed in Industry 4.0 and this move towards a more flexible environment.
Yeah.
It is all about, this last point is exactly right. It is all about that moving from a static single application to more flexible, more dynamic, more open approach to the whole software-defined industry, which is what we are trying to do here.
So somebody says, I didn't grasp the scheduling algorithm. Is it priority ceiling or something similar?
So is that a question for, if it's a question for me relating to preemption, I can quickly go over it again. So the key idea behind the preemption in the Linux kernel is that we are able to interrupt lower priority processes so that higher priority processes can be allowed to run. So if you imagine a process in execution, it could be executing in user or kernel mode, and whenever it requests some data structures from the kernel, it switches from user space to kernel space. So in this scenario, if you are unable to interrupt what is currently running, if you have a higher priority process that must be executed within a guaranteed bounded response time, you're unable to do that if you don't have preemption capabilities. So this is where the tie between preemption and real-time and determinism are all about, in the capability of interrupting the current execution thread so that you can provide a bounded response time to your determinism requirement.
Yeah, I think actually that's going to be one that you might want to follow up on in a bit more detail later to the guy who posed the question. Is there a framework that can be nicely connected to formally support schedulability analysis to formally prove that all deadlines are always met?
Dieter, are you aware of any
I'm not sure I
framework?
understand that question for sure.
I think it's a tool, a framework that you can connect to perform a schedulability analysis, I guess, on the software, like when you're profiling regular software, but to see whether all of the deadlines will always be met when various things preempt each other.
Well, at least at the operating system level, there are tools and performance software that is able to assess how the current processes are running. So for instance, the real-time Linux analysis tool is one way that users can go about seeing the different events under execution, but also there are different softwares, different ways that with real-time at the Linux operating system level, you are able to check the current performance. So whether or not the CPU is able to perform the context switches within the boundary response times that may be required for your specific use case. So for more information on what those different tools or frameworks may be, from Canonical, we will be providing more information on that, but also starting to browse real-time Ubuntu online. The different, what is already available will be apparent, and there are already some resources to get started on this.
But Max, I think so. I'm not sure if that question is quite right in terms of how to think about it, right? So when you were talking earlier about max latencies, right? For industrial control application, the max latency is really what counts in terms of making sure that the real-time workload is processed deterministically within that maximum time again it can use. That maximum time is not something you can completely determine with a scheduling analysis. So it's something that is statistically happening, right? In terms of, hey, if I do that same thing many, many times, right, is my worst case scenario that max latency, right? So I'm not sure of the ability of a scheduling tool to say, hey, how many real-time workloads, if I understood that right, can be handled, will really give you exactly that information. Just maybe I didn't completely understand the question, but that's a word of caution, I think.
And maybe the mindset behind that question comes from the RTOS world, where mathematically proving the response times may be something more familiar to the end users. Here we are in the Linux world, which is different than the RTOS, and what at least real-time Linux with preempt30 does is to make the kernel more preemptive than mainline, but we are still not providing the capabilities of an RTOS system. So we will not have the mathematical guarantee of a certain schedule performance.
Yeah.
Okay. Does real-time Ubuntu support ARM-based hardware platforms, for example, the Raspberry Pi 4?
Yes, so the latest release of real-time Ubuntu is on both x86 and ARM. So those are generic releases. They are not yet silicon optimized. With Intel, as we mentioned, we are working and we will soon release some real-time Ubuntu images optimized on Intel silicon. So for the current release, it is already available that users can go and download and start playing around. Those are not silicon optimized. Those are generic x86 and ARM images. And so we have been testing on both architectures. We are production ready on both architectures, and it's up to the end user to start playing on the different devices that they may have available at home. But soon, because of the collaboration and the ecosystem that we are part of at Canonical, we will soon announce more hardware optimized images of Ubuntu. So Intel is one of those examples. So stay tuned for also those announcements coming soon.
Okay. Does this update meet the needs of ISO 26262, and is it certified?
So we are not certified. If I am correct, ISO 26262 is an automotive related standard about functional safety, and this particular release of Ubuntu, we didn't go under any certification process or procedure yet, but we are in talks with the relevant bodies to start that process. But real-time Ubuntu on its own is not ISO certified.
Okay, there's so many questions here. I don't know where to start. From a software developer's perspective, do I need to change anything in my current real-time application to take the most advantage from the real-time kernel capabilities?
So not necessarily from my perspective. If you're already running your applications on a standard Linux kernel, you can also run it on Linux with preempt_RT, and it should be able to work out just as fine. Of course, if you want to take advantage of the real-time capabilities that preempt_RT provides, so I guess that configuration and tuning aspect that we were referring earlier, it's best to also take a look at the user space level, so at your application layer, to make sure you're taking advantage of those. But on its own, preempt_RT affects the Linux kernel, and it provides this increased preemptable capability. And you should be able to run your applications just as fine, because it is a standard Ubuntu 22.04 kernel with the 5.15 Linux kernel version, with the integration of the out of 3 preempt_RT patches. But it's not a different type of kernel. It is still a standard Linux kernel. It is still 22.04 Ubuntu.
I think the one to add here is, right, if your application is not currently based on using a TSN-based Ethernet network or so, that will also be driving some changes to adopt a TSN-based Ethernet rather than a more legacy industrial bus. So.
Okay, I said at the beginning that if we didn't have time to answer all the questions, you would follow up later. And we have no time to answer all these questions. I've never seen so many questions. So you will be following up later. We've got time for one more question, I think. And also, while I ask this question, Eduardo and Dieter have said that we can put their contact details on the screen so that you can contact them directly. But we are mindful of everyone's time, so we do want to try to finish before the hour. So the last question, and this is one that I would be very interested in myself, is real-time Ubuntu free for anyone to use, and how can I access it?
Right, so I guess I'll have to take that one. So the kernel is available for free via Ubuntu Pro. So Ubuntu Pro is a Linux enterprise subscription that covers different aspects of open infrastructure. And as part of this Ubuntu Pro subscription that I invite you to check out online, we provide a free tier. This free tier is for personal and for small scale commercial use. So this, of course, is in line with our community commitment and our mission to ease open source consumption and access. So every individual, I believe they have access to 3 individual seats, 3 machines on which they can run real-time Ubuntu, and also for their small scale commercial use. So if you go on Ubuntu Pro on your browsers, if you find the relevant information, you'll see it's very easy to get started and launch the real-time Ubuntu images. So once you do get a free subscription token on the Ubuntu Pro webpage, you can very easily on your Ubuntu machine run a Pro attach free token command, and the next command to enable the kernel is just as simple as pro enable real-time -kernel. So if you don't recall what I just said, you can look it up online. All the information is available, but it's literally 2 command line messages, and you can have real-time Ubuntu running for free on your 22.04 Ubuntu machine.
Cool, awesome. Okay, well, I'm sorry, but we have run out of time. So this brings today's webinar to a close. I would like to thank everyone for attending, to give a special thanks once again to Canonical and Intel for their sponsorship, and especially to thank Eduardo and Dieter for their insightful presentation. Once again, this is Clive Max Maxfield. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on the next IoT Central webinar. So until then, from all of us here at IoT Central, we hope you have a wonderful rest of your day.
Thank you, Max, and thank you, everyone.